the cross product of two vectors generates a third vector orthogonal to the first two. All right, so immediately I'm going to pause this. All right, so I got my GeoGebra open. Let me get rid of this plane. Now, let's see if I remember this. I will come up with three variable coordinate, well, three constant coordinate, but using general terms, create sliders for each so I can move it around. And then do another one. And I'm going to create a vector. A. And a vector B. All right, now there's a, and this will impact the actual vector, but that's something that should be kind of familiar by now. You've worked with sliders a little bit. Let's see if I remember the cross product function. Oh, good. It's simple. Vector U and vector V make up the cross product. All right, so I'm just crossing U with V. So I'm going to just kind of manipulate my display a little bit. It, from this angle, does appear as though we do have a vector that is orthogonal to the plane, whatever the plane is that vectors U and V are living on. Right? So I like to do it with sliders because at least we're looking at it in a general sense. It's not a proof, but at least it's giving us a sense of the idea. Because I mean, you never know. I might have just picked two really convenient vectors that allow for its cross product this one time to be orthogonal, whereas any other two vectors might not be orthogonal. But it seems as though wherever I'm moving my slider, it's still maintaining that orthogonal relationship. Sometimes you have to kind of tweak your vantage point just so you can see it. All right, so we have something called the right-hand rule, because there's a little weird application of this. Well, the right-hand rule in itself is, I think, weird, but it works, and so we go with it. But how do we know that the vector shoots off in this direction and not in the other direction? Because it can go downward and still be orthogonal. So what we do is we use the right-hand rule, and basically what that's telling you is that you use your right hand. You have your thumb and your index finger. This is the trickiest part. I can't remember the names of the finger. This one I got. I know the name for this one. Index finger, thumb, and middle finger. So what you do is you place your index finger in the direction of whatever the first vector is in your cross product. So vector U is going in the direction of A. Vector B is going in the direction of vector B is going in the direction of B. So like that. Wherever your thumb would go is where the cross product would go. All right. So that's telling me that my vector should be shooting out in the positive direction. Although this is not really going to be a good representation because it's doing it with a perspective drawing, but I can kind of tweak it so that it looks like it's coming out of the paper. So your thumb is coming out of the paper, and so that's the direction the vector should go. Okay. If I were going the other way, so if I were going from B to A, if I were crossing B to A, your vector would be going in the opposite direction. All right. So I would have to be pointing my index finger in the direction of B, and in order for my middle finger to be going in the direction of A, I'd have to turn my hand over, making my thumb go into the paper. All right. So it's kind of just a quick way of getting a sense of the direction of the resulting vector. I only mention that because when you're dealing with quick mental calculations, it's nice to know, because if I were to, let's say, for example, find the cross product between some unit vectors. So let me get I in there. And J. Now, I and J are living in the XY plane. I already know what's perpendicular to something that's horizontally organized. It's going to be something that's vertical, right? So something living in the XY plane, its cross product would have to be something in the direction of K. It's just a question of is it going up or is it going down, right? So if I create a vector, out of the way, and I could just go vector C, vector D. So I got my vectors there. Without even doing the actual cross product, I can get a sense of what the orientation is of my actual cross product. So without actually computing it, is what I mean to say. So my right hand rule, index finger, if I'm going I cross J, well, let me just, because I'm not overly flexible here, let me just turn that so that it actually matches what I'm capable of physically. Stretch. So we have that. So that's telling me my thumb, if my thumb is going in its natural position, that's pointing out away from the paper. So that's index finger in the direction of I, middle finger in the direction of J. So the cross product should be in the direction of K. So let's check that out and see if that's true. So E, G. All right, and so there's my cross product. It is in fact in the direction of K. There we do have a vector. Orthogonal to the first two. We know which direction it's going. So what some people will do is actually come up with a list of all the different possible ways in which you can cross up I, J, and K, just so you have it. You know, so because we know the cross product of I and J will give us K. You know, so you could just make a note of that and just rely on it. It becomes a fact to them. You know, rather than reinventing the wheel every single time. Especially if I'm telling you that you're going to have open notes on the next test. You know, why not, right? So if I'm going the other way, if I'm crossing J with I, that would be going downward. Again, right-hand rule will get us there. It's just hard physically for me, and maybe for a lot of people. Yeah, I don't even know how to organize. Yeah, this is probably the best I can do. So, thumbs going. Of course, it's got to be like the hand that has nerve pain. So anyway, it's negative K. But then there's another question, like the simple things, like I cross I, J cross J, K cross K. You know, what's the cross product of a vector in itself? Well, thank God for GeoGebra. I mean, it's not quite as good of an invention as things like the undo feature or Control C for copy, Control V for paste, but GeoGebra is pretty good in terms of getting a good sense of things. Yeah, it's a zero vector, right? Because if you're talking about something that's going to be perpendicular to a vector and itself, there's really no way to quantify that except to say at the intersection of the two. So we just default to the zero vector, and that actually ends up being a rule, and we'll prove that later on. All right. Yeah, while we're at, I mean, kind of on a roll here. So we kind of discovered something here. This is, I mean, we get to it later on. It's called the anti-commutative property. If you switch the order of the cross, you're going to get a negation in your resulting vector. So that's kind of nice, which means, well, I mean, it's nice in a lot of fronts, but the main one is that I wouldn't have to figure out, when I figure out like IK, I then don't have to set up a new GeoGebra or do out manual work in order to figure out KI, you know? So I cross K, and I'll write K cross I. All right, so delete. Let me just get my two main vectors here. All right, so vector E. All right, so we have my IJK. Now, I want to find I against K. So again, we know that if it's living in a particular plane, it's going to be orthogonal to that plane. Since this is a vertically organized plane, it's going to have to be shooting off in a horizontal direction. It's just a question of left versus right. Right? So this is I against, I'm doing I against K. Well, physically, I can handle K versus I here, because that's going to shoot me off in the J direction. So let's verify that. I'll do K versus I. K is H. I is E. Go away. I know I screwed something up. All right. What did I screw up? Oh, duh. Oh, you gotta be kidding me. All right. I say K versus I, right? H versus E. All right, so that's going off in the J direction. I would have gone I against K, but again, I couldn't manipulate my wrist enough to do that. But this gets the job done. So I know that going K cross I gets me a J. Oop. So then I cross K would be negative J. Then I would want, what am I missing, JK? KJ? All right, so KJ, that I can do. Shooting out of the page. So in the positive I direction. So that's JK. JK is positive I. So therefore this is negative I. And again, you know, you have GeoGebra. J is G. K is H. So positive I. Right. I'm still working. I'm not there yet. I'm still trying to figure out a way to allow people to use GeoGebra on tests without them cheating in epic fashion. But you know, it would be really nice, I think, and a good learning experience. All right. So anyway,
You know the
sorry, I looked at the wrong person.
the circle thing to easily know about IJK?
Yeah, it's like the imaginary units, like that kind of breakdown. Like you go around the circle.
It's the circle and then it go IJK, go clockwise, it's positive.
Right. Yeah, little mnemonics. Yeah, so the derivation of the cross product formula, it's kind of weird because it's gonna. I mean, there's a couple of ways to do it, but one way relies on us actually kind of having a sense of the cross product, right? So this information, whereas another way is completely algebraic in nature, and you know, that's all well and good. The issue with that is, you know all that space that you have available on this page. We would like use every ounce of it, and then possibly some scrap paper, right? So that's not fun. But what we can do is we can take the vector u, and we're crossing it. Why am I? I just brain cramped there for a second. Almost fell. We need the cross product as a result. So what we need to have is a dot product of u and v. Oh, sorry, u and w, and I think that's an appointment reminder. That dot product should be equal to 0, and VW should be equal to 0. All right, the idea being that if you have a vector in the direction of u, a vector in the direction of v, you'd have W shooting out from there. Each one of those would be themselves perpendicular to the given vector. All right, so that's our start. I'm going to write it in IJK notation. Right, so U is really U1I plus U2J plus U3K. Not 0. W1I plus W2J that's going to be equal to 0. All right, so we're dotting these together. So this multiplied by that, U1, W1, I'll write it as I squared. But remember, it's not a magnitude. They're actual vectors. This is vector I. Okay, so it doesn't have a value of 1. It has a value of 1, 0, 0. Right? So when I write I squared here without the magnitude symbols, that's telling me that I'm writing. It's shorthand for I dot I. So we'll have to dot these together in a second. All right. plus U2 W2 J squared. Although it won't make a difference, but yeah. All right. So that's in our IJK notation. Now, if I take the dot product of I and itself, you can write it out, but it's really, I mean, we're not multiplying magnitudes, but because it is a unit vector, its dot product is going to be 1 anyway. So it really doesn't amount to much, but it's kind of the difference between two concepts notation-wise. So long story short, we get that. All right. Which is nice, but I guess we didn't need the IJK notation to begin with. We're doing the same thing with V and W, but we can kind of cut to the chase there. That's going to be V1 W1 plus V2 W2 plus V3 W3 equals 0. You know what? I think there might be a shortcut to the way I was about to take you through it. Because I did that. I don't want to do that. Goal here is to solve. I think I did elimination. I'm just trying to see if there's any way I can do this with row reduction. I think it might be a mess. Because we have our variables. Plus cancel those out. This might be a disaster waiting to happen if I do it this way. Because okay, so I did it algebraically, and I got for the purpose of solving for W1, W2, W3. That's the whole goal. Is we're looking for a cross product. But I did it algebraically. I didn't do it with row reduction techniques. And I'm trying to see if this is going to play out in a worthwhile fashion if we do it that way. Or if it'll be a complete waste of time. I guess I could just stand here staring at it for even more time. All right, let me do it algebraically, and then I'll think as I'm going. All right, well, if we're doing it algebraically, we're going to eliminate a variable. It doesn't really matter which one, because we have two equations, we want to have two variables. You know what, let's at least try it the other way. All right, so the variables we're solving for are W1, 2, 3. So the coefficients would then be anything that doesn't have a W slapped onto it, right? So U1, U2, U3, V1, V2, V3. Equal to 0. So it's a homogeneous equation. This is either going to be brilliant or it's going to be a disaster. We're going to find out. All right, so row reduction. I want to get rid of that V1 on the bottom. So negative V1 over U1 times R1 plus R2. At a minimum, I don't think I've seen anybody try to do it this way before, so that'll be something for you. Also, there may be a reason why nobody does it this way. Okay, so negative U2V1 over U1 plus V2. Just V1, V2. Did I misread my own handwriting? Yes, no. Yes, I'm multiplying by this guy. This. I'm good? So then the next one would be negative U3 V1 over U1. Now, that being said, I think I made this into a U2 here, so let me fix that. And that is a case of me not being able to read my own handwriting. All right. Whew. I am regretting taking this approach. All right, so that would be U1 V2 minus U2 V1. That feels right. If you don't know anything about a cross product over U1, then what I just said doesn't have any meaning for you. But if you do, it might. But even if you don't know anything about a cross product, you flip to the next page, you see the formula that's there. It's got U1s and V2s in it and stuff like that. So there's something there. We're onto something here. U1 V3 minus U3 V1 over U1 maybe. Well, I'm going to leave off the zeros on the outside just because I'm going to forget to write them anyway. Maybe I'll just backfill them in later on. It's homogeneous anyway, so it's all we're really concerned with. Okay, so we can clear out the U1s. So multiply R2 by U1. All right, so somehow we got to get rid of other things now. All right, because we want to get this row reduced down. So this I want to make into a 1 eventually. I don't know if right now is the moment for it, but that should happen. And this should also become a 1. I can do, well, I can make that happen right now. I don't know if it's benefit. Yeah, why not, right? Divide row 2 by U1 V2 minus U2 V1. So 1 over U1 V2 minus U2 V1 R2. Right. Negative U2 R2 plus R1. So negative U2 U3, no, negative U2 times the fraction plus U3. Over the fraction. Well, last entry is a fraction. All right. Get a common denominator. So that's going to be U3 times U1 V2 minus U2 V1 minus U2 times U1 V3 minus U3 V1 all over shabiggity bangity boom there. Then divide out the U1. So 1 over U1 R1. Still homogeneous. There should be 2 of them more evenly spaced. All right, so let's see what this is. We have W1 equals, well, negative that whole thing, right? Because it's homogeneous, so this would be subtracted over times W3. W1, 2, and 3. So just reverse your numerator. Oh, I missed something. Yeah, the whole other part of it. W2 would be equal to W3. Again, it's the negation that we're subtracting. So I'm going to, again, reverse the sign. So U3 V1 minus U1 V3 over U1 V2 minus U2 V1. W3 is itself, that's a free variable. Yeah. It's got correct stuff in there. So now it seems like we have to select a W3. Well, I'd like to clear out the denominator, so let's let W3 equal U1 V2 minus U2 V1. So then W1 would be equal to just the numerator of your inside fraction. W2 would be equal to U1 times just the numerator of the inner fraction. And W3 is what we defined it as. Some things are going to cancel, I think. Oh, that's U1 V2. Oh, wait a minute. Minus U2, U3, no, plus. Alright, so these go away, right? Alright, well, let me pull the U1 back out. I'll write it as U3 V2. Well, we all have a coefficient of U1 now. Wait a minute. It looks like cofactor expansion. And I swear I'm not hamming this up, but it... Let me just see something. How would we do this? Because it's a product, and then what looks like a determinant. U1 it's got to be like right there with the formula. It's so close. Yeah, right? It's... I could make this negative U1, giving me V1, U3, I'm sorry, U1, V3. Minus U3, V1. Now, how do I make the U1s go to 1? Because if I did, that would be it, right? Well, if I did that, then I think that I'd be looking at, instead of it being equal to W1, it's be equal to something else. All right, well, let me, so maybe it'll come to me. Like I said, it's the first time I've ever even attempted it this way, so I'm kind of proud that I've gotten this far. The determinant shortcut for a cross product, let me show you that real quick. It's on the bottom of page 2, because you'll see how that kind of fits with this.